Alright, good afternoon everyone. So our next speaker is Sebastian Beswick, and he was with the Tasmanian Youth Orchestra and the Hobart Wind Symphony, but now he lives in Melbourne as an iOS developer. His talk today is called Sounds Good. Please welcome him.
Thanks, guys. So thanks for coming today. I work as an iOS developer in Melbourne. I first attended PyCon when it was down in Hobart a couple of years ago while I was studying honours down at UTAS. So today we're going to take a look at what sound actually is and how we can represent it inside a computer. We're going to talk about how sounds can be described in the physical or analogue world, and then how we can use this knowledge to create a digital representation for sound. After this, we'll talk about the basic recipe for implementing a software synthesizer, and we're going to finish up with a live demo where we use PyAudio to build our own simple synthesizer. But first things first, what actually is sound? Now, sound is a sequence of waves of varying pressure that are propagating through a medium, which is usually air, and we can think of these as vibrations. Now, there are three key components that we use to physically quantify sounds. The first component is a thing called pitch. Now, everyone has an inherent understanding of what the pitch of a note is and the relative pitches between two notes. So imagine you've got a guitar and you pluck the higher string on a guitar. You know that it's going to make a high tone. If you pluck the lower string, you know it's going to make a lower tone. Now, the pitch of a musical sound is essentially governed by the frequency of the sound wave, which is really just the speed at which the pressure fluctuations are occurring at. We perceive faster vibrations as higher pitches, and slower vibrations as lower pitches. And this is what we call the frequency of the sound, and we measure this in hertz, or oscillations per second. And as humans, we can hear sounds in the range of about 20 hertz to 20 kilohertz. Now, the second key aspect of sound is a thing that's called amplitude. Going back to our wave description of sound, the amplitude is the degree of change between high pressure and low pressure. But we can think of the amplitude of a sound as its loudness or its volume, and it's basically governed by how much energy went into producing the sound. So when we talk about sounds as being waves, they are quite literally waves, just like that sine wave on the screen there. So they oscillate repeatedly from high to low. And oscillators are very fundamental components in sound synthesizers, as we'll see during the demo. So we've seen that two of the very important characteristics of defining sound are pitch and amplitude. Remember that we can think of amplitude as being loudness and pitch as being the frequency of the sound. So we know what pitch and amplitude are now. What's left over? What's left is a thing called timbre. And it is pronounced timbre, and I really love this definition. So timbre is the psychoacoustician's multidimensional wastebasket category for everything that can't be labelled pitch or loudness. So basically you have pitch, you have amplitude, and then you have all the rest. And this is the thing that actually allows us to quantify the difference between two sounds of identical pitch and amplitude. And sometimes you'll hear this referred to as tone colour. We can break timbre down into two very basic physical properties, the harmonic content, or the spectrum of the sound, and the envelope of the sound. We're going to have a quick look at what spectrum is now, and we'll come back to envelopes later. So when you hear a sound, you're not actually hearing one single frequency, because all sounds are actually composed of many different frequencies sounding together. So for example, when you pluck that string on your guitar, a wave at what we call the fundamental frequency is generated, which in the low string of a guitar, that's about 82 hertz. But that's not all. Also a very large number of higher frequency tones are generated. We call these tones partials or harmonics because they're based on the mathematical harmonic series. So our low guitar string has a fundamental frequency that resonates at 82 hertz, but it also contains energy at all these other harmonic frequencies. Now, the amplitude of these partials or these other frequencies is generally lower or less loud than the fundamental tone. And generally also the amplitude of each partial is different. So basically we can say that a large part of a sound's timbre or tone colour is determined by the harmonic content of the signal. So take a listen to these two sounds here. Now we can tell that both of those sounds were the same note, they were the same pitch, so they were sounding at the same frequency and also at about the same amplitude, but they sounded really very obviously different. This is what the waveform of the first sound looks like, and it's a pure sine wave resonating at 440 hertz, so 440 cycles per second, and that's what its waveform looks like. If we were to perform a Fourier transform on a very small segment of this wave, which would give us a plot of amplitude against frequency, we get a chart that looks like this. Now in this graph here, amplitude is represented on the x-axis and frequency is represented on y. We can see here that most of the power in this sound, that big blue band, is centered directly on the 440 hertz frequency band. So this diagram is very similar to the sort of thing that you would see in, say, a graphic equalizer on your stereo system. Yes? No, hopefully not. Was it very loud at the front?
Well, I don't know, but I'm extremely sensitive to sound, which is why I wanted to join this talk, but that has made me nauseous and unwanted.
Oh, I see. During the demo, there will be a bit of white noise playing. Oh, you're welcome. So this is what the spectrogram of the second sound looks like, and you can see that there's still a large peak at 440 hertz, but there's also lots of power in a lot of other frequencies. So even though we still heard that sound as 440 hertz or a concert A, we heard that its timbre changed, and hence we can conclude that timbre is actually a result of multiple frequencies sounding simultaneously. So that was looking at timbre as being the harmonic content of a sound. And I think really the other important aspect of how a sound's timbre changes is related to how its loudness actually changes over the period of time that the sound is playing. So if you imagine a snare drum and you whack it with a stick, it makes a really loud noise and then gets quiet really quickly. But if you whacked a gong with a soft mallet, it starts off reasonably softly, then it gradually builds up to being quite loud, and it decays and dies down over a very long period of time. So obviously this has a very big impact on what the sound actually sounds like. So you can imagine that two sounds with the same pitch, amplitude, and harmonic structure will sound radically different if their sustain level is different. This has actually been simplified for sound synthesis into something that we call the ADSR model, which is represented with ADSR envelopes, and we'll take a look at what they are now. So an ADSR envelope represents the four basic components to the amplitude of a sound and the way that that changes over time. First component is attack, and this is the time it takes for the sound to reach its maximum amplitude after it starts playing. So snare drum has a very quick attack, gong has a very slow one. Then the decay time, which is the time it takes for the sound to reduce its amplitude until it reaches what we call its sustain or its sustain level, which is the constant amplitude of the sound after the attack's been delivered while the tone's being consistently produced. And finally its release time, which is the amount of time it takes for the amplitude of the sound to reach zero when it finishes playing. Let's actually look at an example of how these ADSR envelopes work by looking at the way a clarinet actually produces a sound in the real world. So that picture on the right there is a clarinet mouthpiece with a wooden reed attached. What happens when a clarinetist gets their clarinet out and starts blowing across that reed is that the reed starts vibrating, which produces a sound that sounds something like this. So when the player starts playing, the they start the clarinet making sound by hitting the clarinet reed with the tip of their tongue, which produces the attack phase, which is a short, kind of sharp sound, and it's why you hear a very defined start to the note. Almost instantaneously after they do this, the air that they're passing through their mouth, blowing into the instrument across the reed, starts the reed to cause vibrating, which actually starts a column of air inside the whole instrument to vibrate. The time it takes for the initially very high amplitude of the attack or the tongue sound to subside to the dynamic level that the player chooses to play his long tone at is called the decay time. And the clarinet sound is going to remain at that sustained level for as long as the player passes a constant stream of air through their instrument. Finally, when they want to stop making sound on the instrument, they just basically stop blowing air into it, which makes the reed slowly stop vibrating, which gradually reduces the amplitude of the sound down to 0, which is the release phase. So that's the ADSR model of amplitude envelopes. Obviously, in the real world, it's quite a bit more complicated than this because musicians are able to make very kind of subtle changes to their tone as they're playing. But ADSR is actually really a very good first approximation to making really realistic synthesized sounds. So now we've seen the basics of how analog sounds work in the real world. Let's see how we can store them digitally so that we can use them inside a computer. Now, in the real world, the properties that define sound, such as their amplitude and pitch, exist as infinite continua. So that means that basically these properties can change infinitesimally to produce a very slightly different sound. For example, we can represent sound as continuously changing radio waves, or distortions in some sort of physical media, such as the bumps on a record groove. And we refer to these representations as analog sound representations. But obviously computers aren't analog, they're digital. So we have to discretize or digitalize these signals before they can be stored for playback within a computer. So that means that the sound has to be broken down into a whole series of discrete parts rather than an analog signal. So obviously in the real world, sounds are analog signals. And when we record them, what we have to do is convert the analog signal into a digital signal in a process that we call transduction. Now, to actually convert an audio signal from a real world analog signal to a digital signal that we can use within a computer, we use a transducer such as a microphone. What the microphone actually does is it takes a measurement of the amplitude of a sound at each discrete point in time and then converts it to a voltage which can be stored as a floating point representation. If this microphone takes a lot of measurements at evenly spaced intervals, then this process can easily be reversed by sending that recorded signal that we took from the microphone to a speaker. And really, speakers and microphones are actually almost exactly the same thing. When we perform this process, it results in the standard form that we use to represent sound within computers, which is called pulse code modulation, or PCM sound. But how can we actually make a sound from scratch? Now, the most simple tone, just like we heard before, is the pure sine tone. So if we generate a sine wave and then periodically measure its amplitude, then we've done basically the same thing that a microphone does, but we've done it algorithmically rather than physically. And we call each of these piecewise measurements a sample of sound. So we have to take a lot of these samples, and we have to choose how often we're going to take them. We call this the sampling rate. Now, up to a point, the higher the sampling rate, i.e. The more samples that you take per second, the more measurements of amplitude that you take, the more accurate the digital representation of your sound's going to be. The sampling rate on this diagram is the horizontal increment. Now, the other factor governing the fidelity of digital audio is how many discrete values we actually use to store the amplitude at each point in time. So that's basically the resolution that we're storing the measurement at. And this is governed obviously by how many bits we assign to store each measurement. and it's the vertical step on this graph. We call this the bit depth, and this sound here has a bit depth of 4, so you can represent every point on that chart as an approximation using 4 bits. Because we necessarily have a very limited number of bits in which to store each sample at each point in time, we have to obviously clamp each sample to a discrete step. So sound synthesis. Synthesis is the process of producing an audio signal by means of applying an algorithm or performing a computation, as opposed to simply producing or reproducing a sound. So synthesis is the act of generating some samples either from nothing or by performing some sort of transformation on an existing signal. Now, there are heaps of different types of sound synthesis, but we don't have very much time today, so we're just going to look at generating a very simple pure sine tone. And this really is very easy. I'm going to summarise this as simply as possible. To produce a synthesised sound, literally all you need to do is create a buffer, put a heap of samples in it, and then send it off to the sound card to have it rendered as audio. So generating the sets of samples that we use to represent the sound in our synthesizer that it's going to play is actually quite simple. And after these samples, we have to send them to the sound card so that it can send audio off to our speakers for it to be played. This is obviously a very low-level interaction, and it's platform-specific. So it's a prime candidate, really, to be kind of externalised to an external library. So we're about to do a demo. For this example, we're going to use the pyaudio module, which provides Python bindings for the cross-platform port audio library. Actually, when I was doing research for this talk, I actually realised that port audio was actually written by one of my mates back in Melbourne, Ross Benchino. And yeah, he's had it ported to Python. So let's crack into a demo. So what we're going to do here is we're going to implement a very simple sound synthesizer from scratch. And hopefully by the end of it, we'll be hearing some sounds that we've created. So the first thing I'm going to do here is I'm going to import the pyaudio module. Then I'm going to initialize a pyaudio object using its standard initializer. Now what we're going to do is we're going to open an audio stream, which we're going to use later on for sending samples to and having that played by the sound subsystem. So what I've got here is just a couple of variables that we're going to use. I'm going to set the audio format to PA float 32, which corresponds to 32-bit floats for a sampling width of 32 bits, which is reasonably standard. I'll set the sampling rate to 44,100 samples per second, which is CD quality 44.1K sound. We'll set the number of channels to 1 to indicate that we want mono audio. So what this means is that the same signal will just be played out of both our speakers in a stereo system, as opposed to usual stereo where you have a different signal being played out of each speaker. And finally, I'll set the should output sound flag to true. This flag just indicates to pyaudio that it should start playing sound immediately as soon as that buffer starts to get filled up. Perfect, so that's our initializer. And once we've opened this stream, we can start writing our sound samples to it. So this is our main audio loop. Now, this is a process that's going to be repeated many times. So we need to generate a lot of samples. We need to continuously generate samples so that we have continuous audio playing. So what happens here is in this audio loop, we're going to generate a whole heap of samples, and then we're going to write them to the sound stream using stream.write. This stream then will, once it has some samples in it, it blocks until it's finished playing all our samples. and it's ready for more. So this loop runs every single time more audio is needed, so we call it the main audio loop. And the main audio loop is really the backbone of every sound synthesizer. I've just passed this out for the moment. We'll come back to it in a sec after we've cleaned up. Clean up, very simple, very boring. All we're doing here, we're asking the stream to stop playing audio, then we'll close the stream, and finally we'll terminate the instance of PyAudio. Now, let's take a look at what we're actually going to put in the main audio loop here. So as I said before, the backbone, the workhorse of our synthesizer is the main audio loop, and this is where the samples are actually going to be generated. Now, PyAudio can run this loop in either blocking mode or callback mode. If you choose to use callback mode, then you'll get a callback on a high priority thread asking you to generate more samples as they're needed. Obviously, this is much more beneficial than running in blocking mode because it means that you can perform other computations while your sound is being played. But for simplicity today, we're just going to run in blocking mode. But if you do want to play with this at home, I do recommend using callback mode. So we'll start off here by initializing a list of raw frames. And this is where we're going to actually store our set of samples. Each time we run through this main audio loop, we're going to generate 1,024 frames of audio, or 1,024 samples. Yep. So go 4 frame in range 1024. Now for the moment, let's just make each of our samples a random number between -1 and 1. Going to import NumPy here as well. And we'll also set the amplitude of our sound to unity or 1. When we produce these samples, they have to be clamped within the range -1 to +1. Otherwise, bad things will happen. If you want a louder sound, you just reduce the amplitude so that they exist within a smaller range. But you should never produce a sample less than -1 or greater than +1. So we'll drop our amplitude in here, and we'll set it to 1. And we'll multiply our sample by the amplitude that we want. So now what we've got here is a list of raw frames, a loop that generates us some samples. Almost. So we'll just append each sample as we generate it to our list of raw frames. Has anyone seen? Have I made any mistakes yet? Thank you. Perfect. Good, glad we got that out of the way early. No, actually they don't. Neither of them do. Hopefully. So, we'll see soon. So now we have our list of raw frames, and all we need to do is write them to the stream so that they can be played by our sound card. I'm going to drop this in here. And all we're doing here is using NumPy to make sure that these are 32-bit floats, and we're writing them just as a string directly to that stream. So let's crack open a terminal. Let's see if we've done any good. There we go, perfect. So what we've got here is some white noise. And now white noise occurs when there's an even distribution of power along every frequency band. So what happened is we filled up our sample buffer with just random numbers, so just junk, and we got white noise. But let's get rid of that terrible white noise generator and look at how we can make our synthesizer produce a nice sine tone. So what we're going to need to do here to do this is we're just going to need to generate a sine wave and then periodically measure its amplitude as we move along the wave. So we're going to create our sine tone at a frequency of 440 hertz, or an A. So it's going to oscillate 440 times per second. And as we move along the sine wave, we're going to start at position theta equals 0, so right at the origin of that sine wave. So what we'll do is we'll take our first measurement of the sine wave and store it in our sample buffer. So I'm going to delete that line there and replace it with sine of theta. And so that's our first sample of the sine wave right at the start, which will give us sine of 0, which is 0. And after we sample this sine wave the first time, before every time we sample it again, we need to move along the wave just enough to ensure that we're taking exactly 44.1 thousand measurements of sound, evenly spaced measurements of sound per second, just like we told the pyaudio initializer that we would. To do this, I'm going to create a variable called theta increment, which is going to control how far we move along the wave at each step. So I'm just going to drop that in there now. The period of sine is 2 pi radians, if we remember back from trig. And when we multiply that by our frequency of 440 hertz to set the pitch of the note to an A, what we do after that is, to get our actual theta increment, is we divide this by the sampling rate, which gives us results in units of radians per sample and allows us to move along that sine wave to ensure that we take 44.1 thousand measurements of it per second. So obviously, after we've taken a measurement of that sine wave and then appended it to our frames array, we need to increment theta by that theta increment variable. And the last thing I'm going to do here is just drop a little. Thank you. The last thing we're going to do here is drop in a conditional to ensure that our theta remains between 0 and 2 pi, because we know that sine waves oscillate periodically and repeatedly. So we could, if we wanted to be a bit more clever, actually, we could pre-calculate, because we know that sine's never going to change. We could pre-calculate all our samples and just store them in a lookup table, and instead of actually computing the value of sine again every single time we need a new sample, we could be much more efficient and just look it up from a table. But we're lazy today, so we're not going to do that. I'm going to crack that open in the terminal again. What do we call it? Synth.py. And perfect. So there's our nice pure sine tone resonating at a frequency of 440 hertz. We can change this frequency here to anything we want. So we change it to 880 and we get a sine wave an octave higher. And similarly, we can set it to any value we want. So that's it. That's our very simple synthesizer using Python and PyAudio. Thank you.